Okay, great. So I guess I'll just give a quick introduction. So Dr. Sujith Ravi is a director at Amazon Alexa AI, where he is leading efforts to build multimodal conversational AI experiences at scale. Prior to that, he was leading and managing multiple ML and NLP teams at Google AI. He founded and headed Google's large-scale graph-based deep semi-supervised learning platform for structured and unstructured data, as well as on-device machine learning. So I'm very excited to hear what he has to say. Yes, I think.
Thank you, Ali, and thanks, David, and everyone else for inviting me. I think it's great. I think I popped in a few sessions, and like you have like some awesome talks, and great job in organizing. And I think it's a great idea to bring people together, especially in this time. And doing this virtually, I'm amazed we keep getting better and better. So excited to be here, just to sort of unpack some of the things that Ali mentioned. My current role, I'm a director at Amazon Alexa AI, where the focus for my team is to build multimodal experiences. So, whether you have Echo Show devices with displays or, just voice-only devices, how do you build, machine learning applications to power conversational AI over that, right? And this involves not just voice medium, but also media, including images and video, etc. Now, before that, I used to lead multiple ML teams at Google. I actually founded several of them. Some of the interesting areas that people may be, already working in this field, or they're interested for their own applications in the industry, or even from a research perspective, are how do you build models at really large scale, and especially in the context of limited supervision. That means it's not always, deep learning has become very awesome at doing a lot of things. How do you do, machine learning at scale, but, when you don't have enough label data? So we built a platform, and that's now used in, hundreds of products at Google and now other places across the industry. And then how do you do machine learning when you have structured information? So think about your applications, not when you're trying to build networks on top of raw text or images, pixels, etc. But instead you have like some interesting information where you have relationships between people, contacts, and like graph structured relationships. Or take knowledge graph, for instance, right? I mean, you have entities and relations and connections between those entities via different types of relations. How do you now use that to power your deep network and get interesting, inference applications out of it? And then finally, it's amazing if you could do all this on the cloud, because we can get better and better, use more resources. But how do you translate some of this into the edge? That means when you have devices like your wearable devices or your phone, etc., which don't have enough computing resources, just as you have a machine on the cloud, how do you build applications for that while keeping your accuracy high? So this is in the vein of the topic that I'm going to talk about. Like some of these, you've already used products, for example, Smart Reply is like almost like an autocomplete like feature, which you're probably, if you're using Gmail, you're already using it, which actually stemmed from interesting research directions and then now are used by hundreds of millions of people. So my talk today is going to be focused more on the last part that I mentioned. How do you do and build efficient neural networks and neural computing machines for the edge and the cloud, but do this in an efficient manner? And the reason why this is an interesting point is we are at an inflection point, right? In computing, in the industry, from a research perspective, whether you take NLP, computer vision, or any other field. What I can tell you, the best way to characterize the motivation for my talk is through this very complicated slide, which I bet everybody will get. So anybody who's doing deep learning or actually using ML models in their application knows we can really push the boundary on doing amazing things on the cloud by using big, large neural networks that are running on the cloud. So motivation for this talk is, how do you do this when you have very tiny devices, right? Tiny from a perspective of memory and compute constraints. And how do you run these tiny neural networks on device while giving you great performance? And on the flip side, you also want to, it's not just about shrinking your models and running them efficiently on edge, but it's also about running your large models efficiently on the cloud. So if you're able to save resources, you probably would want to do more with the same compute. That means imagine you're able to use your network that you use today for any NLP or computer vision application, but instead now you're able to do multimodal inference. That means you're able to process your videos, your images, your text, all at the same capacity. So that's what we're pushing for. And we've started a series of conference and workshops in this space several years ago. And I think, again, going back to the inflection point, I think now is an interesting time when many of these are coming to bear in real world applications. So just to drive down the points a little bit more, right? Why would you want to do on-device, right? I was mentioning this earlier. Specifically for some sets of devices, right? Like your mobile phones or your voice assistants, etc. Privacy might be one of the primary drivers of this. Imagine, you have a developer who's actually, building a bunch of applications, and you're deploying an application, but you don't want the data to be leaving the device because you want to keep that still private from perspective of not sharing it with any ML application or not sharing it with any of the cloud providers because of security reasons. So these sort of this is a key driver for voice assistants and many other areas today, especially when users are becoming increasingly paying more attention to what they're sharing with their cloud providers, with their internet providers, etc. Right? And one of the arguments here is that you shouldn't have to sacrifice any of the amazing progress in AI and using an ML application just because you don't want to share data, right? I think it is possible to do it in a privacy-preserving manner. The second motivation is connectivity. Imagine you're driving through a tunnel and you lose your Wi-Fi connectivity and your assistant just breaks because, oh, we can't connect to the cloud, so we're not going to give you any predictions anymore. That's not a great scenario. The third one is efficiency. We want to make sure that from a memory perspective, from a computation perspective, from an energy perspective, and the carbon footprint, which is the sum total of everything we're doing, how do we keep that very low while driving up the innovations? And lastly, consistent experience, right? When you're moving between the cloud and the device, quite often you don't want an experience to be jittery just because your application runs some stuff on the device and then switches to the cloud, for the more heavy-duty ML application, then switches back. This works in many settings, especially in some of our settings where we have amazing connectivity, but this is not the reality for a large part of the world, right? So we still want to give consistent experiences in those scenarios. So one of the outcomes of this is how do we do on-device natural language understanding? So take a simple application. You're talking to your favorite smart device and asking it to execute some commands like turn on my living room light. Again, if you take this and scale it up to more complex conversations where you're trying to do natural language inference on the input speech that you're providing to the device through your voice, imagine your Wi-Fi stops or the device suddenly cannot process images at the same speed that you would want to do it. It's not a great experience. So the solution to this is we could actually build really fast models in 2020. We are in 2020 now. So we can really build fast models that sit on the device, do really complex inferences, and actually give still great performance, right? You don't have to wait a second or 2 seconds before the device actually understands what you're saying and then executes the command. All these can be done within milliseconds. This also applies to more, a slightly more complex task like conversational AI, where you're actually in a messaging setting and you want to, have your watch help and assist you with the conversations. And this already exists. This was launched several years ago, and this all is powered by on-device machine learning. But again, as I said, it's not just about on-device learning. When you switch to the cloud, we see an interesting trend. If you look at neural computing in the last several years, like about 5 years or so, and just for the sake of argument, let's just stick to natural language processing. One of the biggest innovations in the last couple of years that has happened is the generalizability of what we call language models, which are pretty much the core component of every interesting model that you can see being published today. And what's happened is language models, believe it or not, have entered the billionaire club, right? So from hundreds of millions of parameters, we have now starting to see billions of parameters, and the effect and corresponding effect in quality. We're able to do things much better, make more inferences on new tasks, and generalize better from a domain adaptation perspective. But if you look at what cost this comes at, right, on the right side, all this is also driving up requirements in terms of compute. We need more compute. We need more memory. Which equates to cost. And also, you're running more compute implies you're actually driving up the energy consumption and the carbon footprint. In comparison, I mean, just if you take a second to think about it, your human brain contains about like hundreds of billions of neurons, and we are able to do things much more efficiently, right? I mean, there's an entire field of research which is trying to drive towards this and trying to imitate the cognitive process of the human brain, how it processes information. So in this setting, as I said, it's not just about the on-device setting on the edge, where you have like your watches and your microwaves and your smart assistants all doing more complex things, executing efficiently. But on the cloud as well, at large scale, you want to make sure that the neural networks can run very efficiently from an energy efficiency perspective, from a compute perspective, and memory perspective. How about to get there? I mean, obviously there are a lot of challenges, right? And I'm going to just focus on a couple of them in the interest of time. Hardware constraints, right? You don't have access to a large amount of computer memory in every setting. You also want to make your models more efficient, but not at the cost of quality, because that degrades the experiences. Finally, when we are building up these neural networks, you're often using complex model architectures for inference. Pushing those complex models into small devices, or even on the cloud, making them more efficient is not non-trivial task, especially when it comes to more complex tasks like if you go beyond simple classification to structured prediction and image inference over multiple modalities, etc. So this talk will show you some results on and focus more on the NLP and conversational AI applications, but the same methodologies that we introduce here are applicable to visual recognition and multimodal AI tasks as well. And if you think about designing approaches for this, there's been a lot of work in the past. One of the most naive ways you can think of is if you want to understand, let's say, for example, a simple application for your smart device. When somebody says, play something by Madonna, I want to understand the intent, play song. A simple way is you can start creating a dictionary of mappings between certain inputs and the output category. But for language, you will see quickly this actually explodes, because there's a lot of variance in how we say it, whether it's a person saying it or the choice of words or even the setting. I think you might drop some keywords, or you might say it incompletely. You might even use canonical terms or even short forms, etc. So it's non-scalable for understanding the true intent for a wide variety of use cases. It works when you have a very close vocabulary. And other approaches in the past also include, how do you bring in structure to deep learning models that makes the models much more efficient. But our goal, when we started like a few years ago, was to push the boundary on saying that, but can we instead of focusing on shrinking networks, can we instead build on-device neural networks, design networks that are really small in size, very efficient in terms of inference, and also reach state-of-the-art performance? And the answer is yes. And this is, I would say, one of the most important slides in the talk. we have been working on this for last 4 years, but one of the general or common themes across all of our works has been this notion of generalizable and efficient projection-based neural networks. And just for people on the call, I mean, please check out the ICML paper, and also I will share with you some of the other papers, which if you're interested in learning more about this. And the idea is this: you would build your ML application in the same way, except now instead of using the standard building blocks for your neural network, we're going to use this projection neural network architecture that you see in the center that has a few key properties. It is small in size. That means number of parameters are small, fewer. It's fast in terms of inference. That means when you're running it on your phone, watch, or on the cloud, the inference is much faster. And it can be compiled into a variety of formats. Like, for example, if you compile it into Tensorflow Lite, which is the on-device edge framework from Google, we can actually deploy it to any Android device, and this will give you, an application out of the box for free, depending on what choice of categories of tasks you want to, solve. So one of the earliest works in this line of research was especially for NLP, when we introduced the projection neural network, and it's been used in a variety of applications. But one of the first networks, derivative networks that we created, was what we call self-governing neural networks. And the idea is as follows. Imagine you want to process language. You have a natural language processing applications where you're trying to, let's say, predict the user intent, or where you're trying to classify some text, or whether you're trying to add a follow-up response to an incoming conversation, from a generative perspective. The network is operating as follows. Like, you take your input, and the first layer of the network basically operates over the raw tokens or raw text. And we do things like feature extraction, and feature extraction here is not in the traditional sense of features. It's basically, whatever tokens and bytes appear in the incoming text. And these could be phrases, words, trigrams. It could even be more complex things, skip words and things like that. The key thing here is that you don't need to restrict yourself to any small n sizes or short phrases, etc., in terms of applying this layer. But the magic happens after a couple of layers, where these raw tokens are then converted into a binary vector via what we call different version of locality sensitive hashing. So we call this locality sensitive hashing projection. This was the first work that actually introduced this. And please, again, check the MLP paper for more details on the SGNN network itself, and also the projection net paper for more details on how this works. But essentially what it's doing is takes the raw string, the text, transforms it into a binary vector, such that if you take two inputs, like quick brown fox jumps and quick fox jumps, for example, these two are very close in the string space. Once you dynamically project this in the binary vector space, those resulting two vectors are also going to be close. If you compute the distance, having distance between them, the zeros and ones are going to be absolutely the same in most positions except for a few. So that's the idea. You want to preserve semantic similarity, but do this in a dynamic fashion, and do this without incurring too much compute. So if folks are familiar with embedding-based approaches, this is the first series of works that just gets rid of that completely. So these are embedding-free methods. And then we have other layers and operations that are stacked on top of this to give you a flexible option for the task of choice. So the key point here is the self-governing neural networks. This was when we introduced this. This was the first on-device deep learning model for text classification. And the fast and efficient operations, as I said, like if you look at the bottom left, the figure, what says dynamically generated, going from the input to those binary operations or binary vectors, this is the key, the magic here, right? And it allows us to be super efficient in terms of memory, because now you're just transforming inputs to bits. And this is done dynamically. Regardless, you don't have to store, words in your vocabulary. You don't have to store even subwords or even phrases. So you can use arbitrarily large, input and feature spaces. And the resulting effect is that you can get very tiny SGNN models that yield state-of-the-art performance. And here's an example. So we applied this to a task in conversational AI. For example, you have two people talking and you want to tag the messages with some category. In this case, it's a dialogue act. The first one is a statement. The second one is resembles a back channel. The third one is a yes/no question. This is a standard benchmark data set, the SwitchBoard. And what we found interesting was that the SGNN model outperforms not just traditional HMMs and convolutional networks, which are introduced before that. It even outperformed the state-of-the-art networks like RNNs at the time, and now it's transformers. But it even outperformed the state-of-the-art neural networks, which were almost 100 to 1,000 times bigger. And we still get amazingly high accuracy. Of course, this is not just on one task. If you make the task a little more complex, where you have multi-party conversations, this is the ICSI data set from MRDA, we observe the same phenomenon. And the best part about this is now you don't need to use any pre-trained embedding. So if one of the biggest inventions, changes in NLP was, hey, the use of, pre-trained embeddings and the way to generalize, use that in multiple tasks. But of course, that is the bulk of the storage of your model, right? I mean, you have to load up these gigabytes of embeddings or even hundreds of megabytes, and then stack other operations in your network. Now we're saying we can get rid of the embeddings completely, but still give you high performance in downstream tasks. The nice part about these networks are that you can stack these projection operations and combine with other nonlinearities to get very flexible effect in terms of architecture design choice for your application. So you can do general ML predictions with it. We also showed how you can apply this to computer vision problems and still get like almost 100x reduction in terms of speed. Sorry, not speed, size, and faster, 10 up to 10x increase in speed. And of course, for NLP, we can combine this with recurrent and transformer kind of networks to achieve state-of-the-art. So we didn't stop there for the self-governing neural networks. We published something in 2019, which is called SGNN++. And the idea here is that when we're doing these dynamic operations, if you're smart about how we're going to partition that space while constructing those bit vectors, you can actually get even more speed up. So this was the innovation in the 2019 paper. And like if you compare in the same data sets, you're actually getting better results than even the SGNN model, but able to run much faster. The size might remain the same, but you're able to run much faster. And this is not just for standard classification, input classifications. If you actually use this in voice assistant, for example, you have the ATIS task, which is a benchmark task, is one of the most commonly used one. How far is Oakland from airport from the downtown? The idea is it's an intent is a distance. You want to understand that the user is asking about a distance, and you want to extract Oakland and Oakland Airport and the downtown as places of interest, and you compute the distance and then give the answer. Now for this task, again, we had like the attention-based models were the leading contenders here. When we introduced SGNN++, it got even better performance. So there's something to be said about efficiency. Is not about reducing the size of the model or making it faster. It also improves generalizability and gives you better performance if done right. This was also true, and we can extend this for multiple languages. I'm going to quickly skip over this. Like if you look at our results on feedback, customer feedback. So imagine you get some complaint from a customer and you want to automatically categorize this. Instead of forming all that, imagine your app within the device itself can dynamically do this real time, right? So this is the difference between having a seamless experience, being able to do really amazing things without having to sort of rely on big models or even the cloud. This is an interesting curve that I'd like to show. The nice part is you can actually configure the size of the model versus the quality that you want to achieve. For instance, you can get a model that's about 2.5 megabytes in size, still pretty small, that gives you 95% accuracy. But at the same time, you can scale it all the way down to 100 kilobytes and get 83% accuracy. Now, 83% might be good enough for your setting. And that's the difference. You can actually put that, I mean, you can even get a model that is 10 kilobytes in size if you were to combine it with other operations like, quantization. So this is all orthogonal to other efficiency improvements you can get with quantization and, reduction in floating point precision, etc. You can fit these things on your calculator these days. So, and again, this is a neural network. I mean, I have to repeat this to people many times. This is still a neural network. And in some cases, it's actually a deep neural network. But the way we design these operations are super efficient. So you're able to do things like very fast inference, 3 milliseconds in this case. Finally, just a couple more things. I mentioned word embeddings and pre-trained embeddings are useful to take from one setting, from the language modeling setting, and apply to multiple tasks. You can get the equivalent in the projection case, and this paper is from NACL 2019. You can train this dynamic projection operations component or a sub-block within the projection network, and then transfer that to other tasks like for similarity or for text classification. And the nice part is they're also robust to misspellings and perturbations. So even if the user misspells or types something wrong, you're still able to make a good prediction. And you can extend this from conversations to longer sequences. That's the trend today. You can actually go to much longer sequences. There's a network called Prosecco. If you're interested, check out the MLP paper. And very recently, ProFormer. We're able to get up to 10,000x compression over standard transformer models. Take your BERTs and any of the transformer-based models and get up to 16x improvement in speed. So I think in closing, in the interest of time, one thing I would like everybody to take away is we are at an inflection point in terms of what large models and more and better networks can do. But in conjunction, I think we've been, me and some of the folks have been working on the last several years and laying the foundation for how do you build these next generation computing models, but do that in an efficient fashion, both on the edge and cloud, such that we can get better applications for NLP, multimodal AI, computer vision, and some of the interesting choices, just like you have attention operations, this projection on the fly computation operations are critical to designing such networks. And they give you really fast and accurate models, and they're small in size. So on the one hand, you want to do more with less. So this applies to the cloud. And the other hand, on the edge, you want to do the same things, but at smaller footprint, right? I mean, like the shrinking the model versus building a model of the same size that can do many more things. In both these settings, I think there's a lot of interesting work that is now happening in the industry and in the research community. But hopefully this is something that you keep in mind when you're now starting to use models, ML applications, and building next generation experiences for your favorite use cases, right? With that, thank you so much.
Okay, great. Thank you for the talk. I learned a lot. This is a very kind of interesting area within machine learning, especially for practical use cases. Can you comment on, or are you aware of this, I think, a recent paper that came out of Amazon? It was a BORT by Alex de Winter, and it was using kind of this very, I think to me, novel kind of method for approximations of fully polynomial time approximations. This is something like, I guess, can you comment on how this, does this relate? I guess that's a completely orthogonal type of method to what you're proposing. But what was really interesting about that is that CPU, kind of CPU-based computations are really fast, and the way they optimize it, they had kind of certain metrics a priori that they were interested in, and they were able to optimize with respect to these fine parameters that optimize with respect to these metrics. So I guess maybe could you comment on that?
Yeah, I think there's like BORT is one. There are actually a bunch of methods or research papers that came out which kind of look at this from a different angle, right? In the sense that BERT is awesome, or you would like to use BERT, but again, you can run it on your CPU, or you can deploy it in production because it's just too slow to run, right? People take different cuts to it, right? I mean, where one angle is like, let's try to take BERT architecture and let's try to see how do we optimize it such that the operations, I can simplify some of the things, right? I mean, even if you just simply quantize it, distal BERT is another popular approach where you just throwing away a bunch of layers, right? But that as a result, you get a smaller model. There's also work in from MIT and other places where they're trying to do hardware sort of first, or hardware-driven approaches, where you're saying that I will take parts of BERT or parts of the network and I will run it on the hardware of the target hardware where I want to deploy it. Then I'm going to make some approximations to those blocks based on the hardware. It's not about changing the network architecture itself, but I'm going to make some approximations, and I'm going to and there are many ways to do it. Where we are coming, I think all of these are orthogonal and actually complementary, and people should try to try multiple approaches. But where we are coming from is we're saying if you take one thing out of the transformer or BERT or any of the things, right? Attention is an important mechanism, core block, right? I mean, same thing like convolution for images. We are saying projection is an interesting block that you can apply, especially to take large feature spaces or really complex spaces and reduce it to binary spaces, right? Now, that can be coupled with these choices like, hardware optimization methods. It can be done in the context of BERT. It can be, like, for example, we're able to get 2 or 3 layer, projected BERT, and I think the new version is ProFormer with 2 or 3 layers, the same performance as you would get with a 12-layer BERT network, right? So I think that's where we're going with it, and I will see many more such ideas come out in the next few years. Yeah.
Yeah, definitely. I think in terms of so one approach I guess what I'm curious about is, can you just combine all of these orthogonal methods together and expect it to work?
Yeah.
Or do they actually interact in some way? Are you trying to do trade-offs between different kinds? Is there some optimal kind of balance between them? And in general, I guess, what is the kind of the limit or the theoretical limit of compression that you can apply to these kind of models? Like, what is your
That's an interesting, because I've been, probably working in the space for a while. What we can do from a theoretical versus practical limit, we've been pushing, I think probably even pushing beyond what I had expected a couple of years back, in the sense that I wouldn't have thought that, we could get a model like a network, neural network, deep network. I knew we could shrink it, or we could sort of improve and make it faster, but something as small as tens or hundreds of kilobytes that actually can run on an embedded device, right? You can run it on your Raspberry Pi, or you can just put it in your light bulb. I mean, technically you can fit that thing on your light bulb, right? I mean, it's that small. So imagine the possibilities of, rather than like the Wi-Fi controllers on many of these devices take up a lot of space, and from a chip perspective, and it's also very power hungry. Imagine you could be running very cheap models in every smart device possible, right? That can actually do interesting things. And of course, it's not just that. I mean, you can obviously still connect to the Wi-Fi and do more, more complex things. But I think imagine now turning your microwave or turning your, remote control into like something beyond what we do today, right? Just by hey, pass the voice signal, but it can actually understand your commands and the context.
I guess.
Yeah.
I guess there's some tension between this kind of cloud-based API type, like you have your endpoint behind like a server, and it's just an API call. And I guess your point of view is that everything should be embedded, right? So,
I think one takeaway might be oh, let's put everything on device and distribute, right? I mean, basically distribute the compute. But I think that's one model. It'll work when you have in the IoT setting where you have devices that need to do something smart, right? But you also want on the cloud, right? I mean, you don't want to. I think the goal is not to say that, hey, you don't run anything in the cloud, because far from it. what you want to do is, as we see the advances in neural networks, like bigger models doing really interesting things. I mean, if you like this is actually very interesting stuff in the language modeling scenario. I mean, I've been in the field for 20 years. I mean, since statistical models, I would say in the last couple of years, you've seen the biggest improvements, right? You want innovations like that, but can you do that more efficiently, right? And you want to do that in conjunction with the computer vision, like inference, right? I mean, do the multimodal. That's where I think the field is headed, right? And to answer your earlier question about, are these methods complementary? Yes, they are, but you may not see additive improvements all the time. For example, I think I count like probably 20 or 30 papers written on how do you distill versus prune, right? Should you take a big model and then prune it and distill it, or do you start from a small model and then, you know, and there have been papers that actually talk, hey, we get results one way or the other way, right? Here, what we're trying to do is that if you get these building blocks right, especially the projection operation, as I said, it theoretically is basically taking a high dimensional space and squishing it into, and you get actually theoretical bounds on that space. If you use that to design some of the layers in the network, you get really efficient models, right? You can combine that with quantization. You can still train that in a distillation fashion, as the first paper that we published, right? To improve your performance. You can prune it further. You can do all those things, right? But note that you may not stack everything together and get like an additive, you know, sort of a factor there.
I see. So for a practitioner, is this something, right? I guess I guess another kind of element too is the hardware acceleration, and then are you fitting the hardware to the algorithm or the algorithm to the hardware, and how do these things kind of co-evolve? Like, you know, Apple is coming up with these M1 chips of dedicated compute that seems to be kind of on for embedded devices or mobile devices having dedicated kind of computations for machine learning kind of applications. That seems to be a big direction. So how do you see that evolving?
Yeah, I think that's the other half of the coin, right? I think like when we did the on-device workshop, I think one part is like software-driven, algorithm-driven. The other one is hardware optimization. I think they go hand in hand, like you said, the M1 and like other, you know, sort of, you know, innovations that are happening in the hardware space, like even in AWS, etc. I think these would be interesting drivers for pushing the boundaries even further. The key though for practitioners are what is the like min viable or like sort of the language that you can speak or like operate in, where you can take your models and translate it into the wins that you see on a new hardware, right? And there are a bunch of interfaces being developed. Like for example, the projection, like you are actually getting binary vectors. Now, whether you use the, you know, squish it into 4-bit blocks or 8-bit blocks versus it's orthogonal. One thing I would say though is, in my experience, the scale, right? You get super high improvements in hardware and you also software, all these other methods. But the algorithmic innovations are the ones that give you a order of magnitude reduction, typically. But of course, it doesn't come cheap either, right? I mean, it requires a lot of work and a lot of thinking and many sort of trial and errors and things like that, right? And that's why we found with the projection operation, right? But I would say that there'll be many more such kind of things. And then the key would be, how do you take those blocks and make it run efficiently on GPU, right? Or ARM devices, or even the new, like, you know, the Apple devices, the M1, or like on the Inferentia, on the cloud, right? I think that will require both hardware and software engineers to be co-developing this. I think this is where open source is amazing. I think it's been a big driver, and you will see many more like interesting directions and like new ideas coming out in that space. I would argue open source is the single most interesting and most important reasons for the propagation of deep net and like, you know, sort of the impact of deep networks, right? If it didn't exist, we'd probably be 5x better than probabilistic graphic models. I mean, maybe, but not at the scale.
Right. I'm certainly, I guess, in terms of these SGNNs and the kind of bit operations that they perform, is there, well, for one thing, how do you backpropagate through these kind of things, and how do you update these? You have like these LSH codes. Yeah. You have to update them on the fly. So there's some very kind of practical issues about like implementing it, right?
Yeah. That's a great question, because I think our first series of models in the projection family, the projection itself would be static, right? I mean, it actually operates over much larger spaces, but that itself, the dynamic computation, would be static. And then the backprop sort of operates on top of the binary vectors, right? So you're now learning nonlinear combination of the binary. Then we actually extended that in our more recent models, right? ProFormer and other places, where you're actually making the projection function also differentiable by the choice of function, right? So it's, and quite often this is like very, very non-trivial, because like these operate in very high dimensional math and high dimensional spaces, and they don't have differentiable, gradient updates of the equivalent that we know for like standard convolutions or dense networks. But there are some interesting extensions in the more recent ProFormer and Prosecco, etc., where you're combining the, let's say, attention and the projection operation and making both of them differentiable. And that, as you can imagine, gives you better performance, because now you're able to operate and say that, oh, what type of projections or combinations are interesting, right, in the context of the given task and the data, rather than saying that, okay, I fix my input transformation through the projection and then do everything afterwards.
Okay. I guess I'll look up some more questions from the chat. I guess I'll keep asking questions until you're tired. So for these SGNNs, how much fine tuning is normally needed, especially if you're trying on new data sets and you want to see this advantage that SGNNs have over state-of-the-art architectures? Are you spending a lot of time fine tuning and optimizing? Does your data sets, do you kind of get the same advantage from pre-training that transformers have, and you just have to fine tune on a small data sets? How does that work?
Yeah. So from a fine-tuning perspective, like at least the first series of experiments that we did, like after the meeting data set that I showed in, on one of the slides, right? The parameters were exactly the same. We didn't do any fine-tuning. But of course, I mean, like, you do want to change the complexity of the model, condition on the task and like the compute and the memory that you have available, right? So based on the resource constraint. So from that perspective, there's, actually one or two parameters where you say that in the projection operations, right, there are multiple functions that are being applied. So you're technically generating, it's not a single operation, it generates this via like T operations. So, and each of those T generates a D-dimensional vector. So now you can vary the T and D essentially to say that, okay, do I want like a longer binary vector, or do you want like, fewer projections or fewer bits per operation? Those are two components. And that has an effect on like the model capacity, if you will, on, for a given task, like for a simple task, like conversational tasks, like classification. I mean, you can just use standard like 128 dimensional or 128 operations, etc., and that will be still giving you a model that's under 1 meg. Now for longer sequences, the more ProFormers and Proseccos, etc., these are combined with other operations like recurrence or attention, right? So you obviously have choices in those parameterization of that. The interesting thing is we haven't seen a big need in terms of hyperparameter optimization for the training itself, like, switching between Atom and many other things. So from that perspective is good. I think the key here is like, it's up to you. You can actually take, run the same thing with 10 different values and you will get 10 different models like I showed you on that plot. And you can plot the, size versus quality accuracy. You can even pre-compute that. You can even derive that how much, computation you're going to do. If you take that T and D, that's basically, T times D bit vectors that you're going to generate. And that will give you an idea of the space that you need.
Those are the kind of primary hyperparameters, and you're just kind of playing around with this. I see. Okay, I guess in terms of kind of edge devices and kind of these, in terms of like Internet of Things, do you, I guess what kind of algorithms do you see being run on these things? SGNNs, can you run SGNNs that do kind of speech to text, or what kind of edge devices? I guess.
Yeah, actually, and it's if you're using an Android phone, some of these things are already, you're probably using it. You just don't know that it's embedded in some of the applications. So you could run, like, I mean, SGNNs are like, the end of the spectrum where you get the highest compression because the models are super small, right? I mean, even the ProFormers and the Proseccos, we can run on much, but you can actually run it on speech signal. And these are, you can even go up to, hundreds, even thousands of tokens in length. That means it's probably more applicable to speech than language, because on your phone, you probably are not going to look at 1,000 tokens in a single shot, right? I mean, I think you probably have from a cognitive perspective and also from your visual cue, right? The screens are small, the UI is small, but you could run like even speech plus language. We had some work in this direction as well, like, where you can combine speech plus language as blocks, and each of them will have some interesting design choices where you say that from the language perspective, you're able to compress the vocabulary space and the sort of the cardinality of the context that you're using to make the prediction. From the speech, you're actually able to compress the length of the speech signal to some extent instead of operating over the entire length. And in conjunction with quantization and other things, and they give you like some remarkable things that you can run it on your phones for sure. You could run it on even your watches. So like the Smart Reply, which is the automated response, are actually running on Android watches, by the way. So that was one of the earliest ones we released. You could run this on your Raspberry Pi, although Raspberry Pi is increasing its capacity these days. But I think like some of them can be run. Technically, I believe your light bulb, you could talk to your light bulb just like you talk to your smart device and get.
Are you saying they'll be always on? Is it kind of, or is there a trigger where it's like Alexa, you trigger it, or is it running in the background?
Yeah, I think you would. It's not. Yeah, it'll not be like one model that's going to be on all the time, right? You would still, I think, just to be again efficiency conscious, etc. You would have maybe a cheap model that's like sort of latently waiting to be triggered, right? I mean, that'll be a super kind of like the wake word, right? Like you said, Alexa. When you say Alexa, right, the device listens, right? So that'll be the cue for it to trigger the rest of it, but on the other hand, I would also say that because of the high throughput and the efficiency you're able to get, there might be a scenario where you never have to say a wake word, right? I mean, everything is processed on the device and you're continuously talking to it. I mean, of course, there's also signal to noise. You have to remove the background information, right? But I think that might be an interesting direction as well. It may not be for every single thing you say, but maybe in the context of like some limited applications, you might be able to run that, like always on, right? Ambient sort of.
Yeah, I see. Okay, interesting. I guess in terms of kind of NLP on edge devices, what are the challenges with building solutions for the edge, especially for like low resources, that kind of thing, low resource, both in terms of compute or maybe low resource language in terms of kind of data? Yeah.
Yeah, I think the low resource NLP, I feel, is harder than like its traditional counterparts like vision, right? I think computer vision, I would say, like, and I've been working in computer vision as well, was slightly ahead in the phones, and the cameras started doing some very interesting things before you could do all the cool things with NLP from an application perspective, right? And that's primarily driven by, if you look at inputs are always like pixels, right? I mean, this is continuous spaces. So the kind of optimization and hardware and everything that went into like processing these, like, sort of made leaps and bounds advances. NLP had the challenge of, you could say the same thing in 100 different ways, right? And it's very hard to disambiguate, right? I mean, but it's at the word level, phrase level for a given user. Now you have emojis and like all kinds of expressive things, right? So, but we're now starting to see the trend where like powerful models can actually disambiguate the context, right? I mean, you see this for the language models now made a big leap. And I think we think similar thing can happen on the edge as well, where the challenge is like identifying those things like equivalents of the traditional language models or the transformers, if you will, right? And that's why I think a ProFormer and like the projection-based networks are good candidates for that. They become building blocks, right? Core blocks. Then you can now customize that for your own application, change it, just plug it in. But it also requires you to take that block and maybe in TensorFlow Lite or one of the frameworks and pipe it into an Android or an iOS application, right? I think there's some challenges in the developer aspect, right? But I think we've tried to simplify that over the last couple of years with like more frameworks, like, we launched TensorFlow Lite, but you see many other things coming out in the same vein, right? Makes it easier and easier.
Right. I guess I'll start winding down, but for let's say for SGNN plus these SGNN class of models, is it? Do you see only inference gain in terms of kind of inference and kind of, let's say, like the compute, like the forward pass? Is there a time gain? Do you see the same kind of gains in terms of training time? So let's say you have these, they're more efficient in terms from a computational point of view, but you need more data to train them, or they're not data efficient. Like, how does it interact in terms of kind of the number of samples that you need, or just training times in terms of how long you have to train for?
Yeah, I think that's a great question. So I don't remember which paper. I believe either we did or we I have to dig it out. But we did actually publish some results in one of the papers where it's not just for. I think the original motivation was for doing faster inference and like cheaper inference. But as a result, because these some of them, the later versions are differentiable, we noticed that you could train these things super fast, right? So now we're not talking about this distillation setting, but you're saying that on training data, the same training data, you would have to run it for, let's say, maybe 10 epochs or something like that. Versus a large model, I mean, by theoretical, analysis, you could say that you need to run it at least for X number before you converge, right? So this is the difference. So it's not just for the forward pass, even for the backward pass, and like even for training, these are super fast to run, right? Now, whether you want to take, let's say, your SGNN, and then also sort of couple that in a distillation cells thing with a really large model. Take GPT-3 for example, right? And then you want to say, okay, I want to make my SGNN super like on steroids or something, right? And then you can actually add the distillation kind of setup as well. But I think fundamentally all the operations, whether it's training or inference, like forward pass is cheaper, so you could run it faster. And same thing also for smaller data. That's the other part. Interesting finding was that you could actually see it's more robust, even though it's trained on less data, because you're not memorizing too many things, right? You have your parameters, right?
So from a practitioner point of view, I guess you're saying I want to use SGNNs, I want to use them on these edge devices, mobile device. I should be distilling. I should have a larger model.
No, I would say that if you have classification, sequence labeling, conversational application, they can be just used out of the box. If you want things like inference, like GPT-3 does, right? I mean, you're able to now program and do zero-shot learning on many new things. Then you want to sort of boost it up with a really large, powerful model, right? That it can learn from even further. It'll benefit from that. But if it is a standalone task, I think for most of these, you can just use it out of the box.
Okay. I guess stop me whenever you want. I still have lots of questions in the chat that I could ask you. But maybe 5 more minutes. Is that good? Or
sure, yeah.
Yes. Okay. Sure. Okay. I guess can you comment on kind of SGNNs and do the same gains of actually hold on, let me see. Okay, I guess in terms of SGNNs, you've mostly applied them to neural nets, but can they be applied to kind of, I guess, other tree-based models, graph neural nets? Is it just the layer that you're this is just kind of like a, how would you say, a building block that you can apply to any model that you want, or is it very architecture specific? That, like, is there something architecture specific that makes it work? Or
I see that the question from the decision tree. Yeah, it is a block, so you could apply to non-neural models as well. And in fact, I mean, if you just remove the non-linearities out of some of the layers, like technically you could plug those in and get the kind of same benefits. Now the question is whether, when you're training them, right? I mean, whether you're going to get the same sort of effect as you would see in deep neural networks, right? Because like in combination with nonlinearities, you're able to learn certain functions much better than like, traditional type of ML models that use simpler functions. But technically, yes, you can use it.
Okay. Okay, great. Okay, I guess one more question. So I guess for comparing TF Lite, TensorFlow Lite and Apache TVM, Amazon SageMaker Neo, can you kind of do maybe like a comparison, a trade-off? I guess someone is kind of interested from kind of like a practical point of view.
Oh, I think both of them are actually the different ones, the TVM and the TF Lite, and they all have different spectra where they operate. Like TF Lite is like the open source version where you're trying to compile and then it works, seamlessly with. If you're using TensorFlow, then you probably want to use TF Lite to sort of couple your applications with that if you want to push to the edge. Neo and on the Amazon side, I think if you are a cloud provider, cloud developer, I think it's a great choice because you now have many tools at your disposal where you actually can operate. So I would say they use some fundamental blocks in a similar fashion, but it's more like a developer choice. Like which one are you more comfortable, right? Where you're able to, deploy your applications or you're already building on top of. And then, but nowadays you also have converters between these frameworks. So I think that makes it easier.
So it's easy if I'm using something like I don't know, something on Google Cloud, I can easily just import my project into Amazon and can continue.
Yeah, like the different communities are now making it more and more interoperable. I mean, just like you could switch between some models between TensorFlow and PyTorch and MXNet, etc. I think there are similar kind of things happening.
Like interoperability, yeah. Okay. Okay, very, very great. I won't take up any more of your time. I've learned a lot, and so has everyone else. I guess I'll just I'll applause. I'll give applause on behalf of the audience. Yeah.
Alrighty, thank you so much for having me. Excited and congrats again for organizing a great summit. Looking forward to some more talks, but great to be here. Thanks.